Hello, this is Alex Lamb. Today I'm interviewing Kevin Roth from ETH Zurich, and we're going to be talking about the issues related to stabilizing GAN training, especially his work in this area. So first, can you give me an introduction about yourself and what you've been doing?
I'm Kevin. Hi. I grew up in central Switzerland. I then studied theoretical physics at ETH, and about 1.5 years ago, I got this joint PhD position between Thomas Hoffmann at ETH Zurich and Sebastian Novatzin at Microsoft Research.
What kind of theoretical physics did you do?
So during my studies, I mostly focused on quantum theory and statistical physics. Towards the end of that, I moved towards network theory and also slightly into machine learning, all that stuff.
Could you describe the GAN stability problem and what do you think are its main causes?
In the GANs setting, we have two players. So we have a generator that tries to generate realistic samples, and we have a discriminator that tries to distinguish between generated samples and a data set of real samples. Now, in the basic idea of the GAN algorithm is that these two players, the generator and the discriminator, successively train each other. So let's say this is the generator and this is the discriminator. So as long as the two players are more or less equally powerful, training progresses, right? If the vertical axis indicates how good they are. And then the GAN stability problem arises if one of the two players, typically the discriminator, gets much better than the generator. So in this case, the discriminator gets much better, training stops, and then there is no more gradient signal flowing between the two players.
Would you see it mostly in terms of the discriminator becoming saturated, or?
I would say it's mostly a problem of the discriminator being too powerful. And
Yeah.
I think it has a lot to do with what was pointed out in Martin Archovsky and Leon Bouteau's paper towards principled methods, where they say the underlying cause of this instability is basically that the two distributions, the generated distribution and the real distribution, do not have overlapping supports. So
Yeah.
in this case, the discriminator has a super easy task at perfectly separating the two distributions, and what happens is it will be kind of heavy-sideish without any meaningful gradient signal.
What do you think about progress on the GAN stability problem, and what methods do you think are the most important of those that have come out?
I think there has been a great lot of progress on the GAN stability problem. So zooming out a little bit, maybe some of the more influential works that I know about are the one I mentioned from Martin Archovsky, the principled methods for training GANs, where they introduced this kind of problem of non-overlapping supports. Then there was the Wasserstein GAN problem, where Martin Archovsky, Sumit Shintala, and Leon Bouteau proposed the Wasserstein metric as a GAN objective. Improved techniques for training GANs by Tim Salimans et al., where they proposed some heuristic measures, like, for instance, trying to match the statistics of the true data, which helped a lot to stabilize. And then more recently, there was also Ishan Gulrajani's work on improved training of Wasserstein GANs, where they, similar to what we do in the newspaper, propose a gradient penalty for the discriminator. Limited influence on the support of the generated distribution, but what we can actually influence is the objective through which the discriminator or the two players are trained. If you think of the GAN objective, then you have this the supremum over the discriminator. The effective cause of this instability, or the cause we can affect, is supremum is taken over. What kind of function class the supremum is taken over. So if it's a completely unconstrained class, there will be all sorts of wildly behaved discriminators in there. But if it's a kind of well-behaved, smooth class, then I think we can hope to be able to stabilize this GAN training.
Do you think there are any significant disadvantages to the WGAN?
Well, I think the WGAN was introduced at a time where the stability problem was maybe the major issue with GANs. But yes, I do think that there are some significant limitations. Perhaps the most significant one of them is that the Wasserstein GAN depends on a metric in data space, typically a L1 or L2 metric. And the problem with these metrics is that they are really a very poor fit for how humans perceive similarity. For instance, take the example of a pixel space. If we have an image slightly darker, this corresponds to adding a constant to each pixel value. And then the L2 distance of the difference between the two images might be quite large, even though the semantic properties are really the same, and even though it's for a human, it's barely perceptible, this difference. So this dependence on the metric, I think, is one of the limitations of Wasserstein GANs, which occurs when you go to non-Euclidean spaces, for instance. Since if you have word embedding spaces or something, then it could be that the different dimensions in your embedding space scale differently, right?
Yeah.
So the metric might not make sense there. Whereas, the F divergence-based GANs, they do not suffer from this limitation. So to me, it's really when you talk or when people talk about which distance or divergence induces a weaker topology, I think the question we should ask is also, what is the quality of the gradient signal that we get from these divergences or different distances? If the slightly darker image has a very different Wasserstein or metric, then the Wasserstein objective might tell you you're still quite far from the true sample, so you still need to move a lot of probability mass in your data space, whereas actually it's imperceptible to a human. So
I understand that's what the Wasserstein metric looks like mathematically, but I'm having a hard time thinking about how that would actually apply to the GAN specifically, like for a WGAN GP, for example.
So you mean there's this kind of gap between the primal formulation of the Wasserstein GAN that explicitly depends on the metric, and then this dual formulation where you have the supremum over these critics in the Wasserstein case? I mean, if there is no gap, if the gap between the primal and the dual is zero, so that would be for an optimal critic. Principle, your Wasserstein distance would measure this kind of metric, right, between, the generated sample and the true sample.
The discriminator is still a network, so it's going to, if two things are closely related to each other, just because of the way a convnet is structured, it's generally going to see them as similar, or it's going to process them in a similar way, especially if you have max pooling.
One of the motivations for using these GANs, the Wasserstein GANs, was to say that they have a gradient almost everywhere, right? The example that Martin Arjovsky gave in the Wasserstein paper is this learning two kind of linear functions.
Mm.
And then you could show that if you use the Wasserstein distance, you get kind of a gradient signal that tells you how to move these two together. Having a gradient almost everywhere relies on this kind of notion of having a metric in data space. But the disadvantage of this is what we discussed, right? So that it doesn't really reflect how humans perceive similarities. But of course, then when you use these convolutional nets, there might be a kind of a gap between theory and what's happening in practice.
Going into your NIPS paper, regularizing GANs by stabilizing activations, that's the name, right?
It's called stabilizing training of GANs through regularization.
Okay, yeah, I reversed it there. Can you explain what the dimensional misspecification challenge is?
Yeah, as Martin Arjovsky pointed out, if the two distribution, the generated and the real one, live on low-dimensional manifolds, their support will not overlap with probability 1, right? So the probability that they overlap is 0, And this means that the optimal discriminator can perfectly distinguish two distributions. So let's say we have true distribution, which has this kind of triangle shape, and a generated distribution that have non-overlapping support, then the optimal discriminator will be this kind of heavy-sided, infinitely steep function. And when you look at this, or when I looked at this, I thought, okay, why don't we use a gradient penalty that kind of prevents the discriminator from being infinitely steep, right? So that it behaves more smoothly between the two distributions.
How does the problem relate to dimensional misspecification, or could you?
Yeah, so the dimensional misspecification is exactly this kind of, if the two distributions live on low dimensional manifolds, then they will be easily separable by an optimal discriminator. And this is actually also what we observed in this 3D GAN experiment, where we have a 2D mixture that we project in 3D space. The generator actually never really manages to completely constrain its mass on this 2D subspace. So it will always have a kind of component orthogonal to this submanifold, and this is just too easy a task for the discriminator to distinguish. So in practice, the discriminator will be really heavy-sided, so it can, with very high confidence, tell that the samples are not real. It's very easy from this dimensional mismatch.
I see. So it's like the full space.
To separate the two distributions.
So it's like the full space is like a 3D thing, and the actual data is like a 2D disk in the 3D space. And you're saying a generator, it's very hard for it to learn to literally put all of its density onto the disk.
Exactly. Essentially on a submanifold that has measure 0 in the entire space.
Right.
It's super trivial for a discriminator to figure out what is real and what is fake if the generator doesn't manage to constrain it perfectly.
And you're saying that the gradient penalty prevents the discriminator from becoming like this heavy-side function type thing?
Yes, because essentially you penalize this infinitely steep heavy-sided discriminator, right?
If like the generated points are like at like a point like -3, and the real data points are at like 3, like they're literally concentrated at these 2 points. If I apply the gradient penalty right at the data points, if it is like a heavy-side type function, I can make the gradient penalties 0 just by making it flat right at the data points, but it's actually very steep away from the data points. Over the course of training, it's actually hard for it to produce this steep curve without there being any data points there.
I mean, typically also this kind of heavy-sided shape is something that we observe towards the convergence of GAN training, or at least once the discriminator and the generator are fairly well trained. So maybe in the beginning, if the data or the generated data looks more or less random, you don't see this kind of heavy-sided discriminator. But as soon as you do produce something that looks already very good, the discriminator starts to focus on ever smaller differences. And I think that's then where this kind of heavy-sided discriminator issue comes into play.
If you could make the gradient penalty apply everywhere in the space versus like just at the real and generated data points, do you think that would be better? Or
there were approaches like, I think, the Dragon paper and also the Wasserstein gradient penalty, improved Wasserstein paper, that kind of
they add noise, or they
interpolate between real and generated data, and impose this gradient penalty somewhere along this trajectory. If this turns out to work very well, I guess one could ask, what is is there a theoretical reason for this? So far, I mean, from just doing the theory, there was nothing to suggest that this, or should be the way to do it. But I guess heuristically, it could very well make sense to penalize somewhere in between. But typically, I think the way I see it is, what you care about is moving your generated samples closer to your true samples. So what you really care is kind of the shape of the discriminator around your generated samples. So if you penalize the discriminator at the generated samples to make it smooth there, then you will also get a meaningful gradient, right? So, I mean, penalizing somewhere in between might make the generator smooth, let's say, more globally, but actually what you need to be able to update your generator is really the shape.
Really can just be local around the generator.
Exactly.
You explain how adding noise to the real data distribution and the generating distribution regularizes GAN training. And then if you add noise to both, does the estimator that you have still recover the right distribution, if that makes sense? So like if I'm fitting two distributions to each other and I just add noise to both of them before fitting my estimator, like the first question is how does that regularize it? And then the second question is if I find the right distribution, is it guaranteed?
Sure, two very interesting questions. So the first, I would say from a theoretical perspective, the problem is that the F divergence is not defined if the two distributions do not overlap. So if the generated distribution and the true distribution do not overlap, the F divergence is not defined. And the standard solution there is to add noise, which mathematically is equivalent to convolving the corresponding densities. And as soon as you convolve those two densities, they will now have support in the entire data space. And the optimal discriminator that you learn from this will be smooth.
Yeah.
So the main contribution of our paper was to show that this convolution or adding noise is actually equivalent to regularizing the discriminator. So instead of explicitly adding noise, you want to have a regularizer that has the same effect, even if you don't explicitly add noise, right? And this stabilizes GAN training because the discriminator will no longer be able to trivially separate the two distributions, even if they live on these two kind of lower dimensional manifolds, right?
Yeah.
So the discriminator has a harder time telling them apart based on some, like based on the fact that these two distributions have support on low dimensional manifolds.
I see.
And then the other question, whether we can still recover the right Q distribution, I think is particularly interesting because so what we observed experimentally is if you explicitly add noise, then this really degrades the quality of your generated samples quite quickly. Whereas if you use the regularizer, you don't actually add noise, right? So the noise is no longer part of the generative process, but instead it's really just optimizing your discriminator over a smoother function class. And moreover, I think with the regularizer, what you can do is you have this noise amplitude gamma, and during training you can anneal this gamma away, right? So that and in principle, I think it is possible to recover that the generated distribution Q is equal to the empirical distribution.
But you're saying theoretically you can recover that, but in practice, when you add noise, it's difficult to.
Exactly. So in theory, you do have, I think, the possibility to recover it, but maybe the more relevant question is, do you actually want to recover the empirical distribution? In the sense that your empirical distribution might just be one, instantiation of the unknown underlying data distribution P, and maybe you don't want your discriminator to kind of overfit to this one instance of an empirical sample, but instead maybe you want to learn a discriminator that generalizes somehow. And this might also allow you to generate samples that could have come from the unknown true distribution.
Is there a reason to inject the noise in X space rather than, or I guess in addition to the hidden states of the discriminator? And do you know if that's been explored?
Right, so injecting noise in X space gives you also gradients with respect to the input X, right?
Yeah,
And so let's say the beauty about injecting noise in X space is twofold. So first of all, you solve this dimensional misspecification problem that we talked about earlier.
yeah,
And the other thing is that these gradients with respect to X, they do not depend on the parameterization of your neural network. So
yeah,
this is kind of what we call an intrinsic regularizer. It more directly acts on the function itself rather than acting on the parameterization of your neural network. And so I think these are two very interesting advantages. And injecting noise directly in the hidden space, I mean, I did not explore it, but I can imagine that if your hidden space is very high dimensional, you run into the same problem of when you explicitly sample this noise, it's very ineffective, right? You would have to sample a lot of random vectors and add them to kind of, due to the curse of dimensionality, to kind of cover this hidden space somewhat uniformly.
One thing I'm curious about with this, but also with other things we do to regularize GAN discriminators, is if you just take a normal classifier and you apply these types of regularizations to it, does it make the classifier's quality about the same, or does it like limit its capacity to some extent?
You mean in terms of accuracy?
Yeah, yeah. Like if I just train like a normal classifier on it, and then I add the gradient penalty, does that hurt its accuracy?
Uh,
Is it about the same?
I mean, what you actually want is that it does not hurt your test set accuracy, right? So the hope is that if you add this regularizer, it will make, so the hope is that the discriminator will generalize better to unseen samples.
Yeah,
And I mean, it's always a trade-off between robustness and accuracy. So, I mean, of course, you get the best accuracy if you just memorize your entire data set. But in the case of GANs, this might be one of the reasons why training gets unstable. Whereas if you are robust, then necessarily you have kind of, or you're willing to incur a kind of cost of maybe having a slightly reduced accuracy.
yeah.
On the other hand, being able to better classify completely unknown, unseen samples.
I could see the gradient penalty helping in practice when you add it to a classifier, but like conceptually, I could also imagine stuff where points of two different classes, they actually are like pretty close in the X space. And then by adding the gradient penalty, maybe it gets hard for it to put the decision boundary right between them. Although maybe that doesn't happen. I'm not sure.
It's a good question. I mean, also,
Or it's hard for it to make the decision boundary as sharp as you'd hope for it to be.
but then the question might be, if those two samples are really that close, why do they have a different label in the first place, right? And then, of course, you would like to have a kind of smoothly varying discriminator. So what we saw in practice is that if you don't use the gradient penalty, then your classifier will be kind of high output on the one class and then quite suddenly drop and give you a low output on the other class.
Yeah.
And then what you actually want in practice, I think, is a smooth transition so that you know, okay, we are now in a regime where the classifier is uncertain. You know, uncertainty means he's kind of in between both classes, which tell you, I mean, for all these classification tasks,
Yeah.
it does not only matter whether you output whether the best prediction matches the true label, but you should also take into account how certain you are when you make these predictions.
Mm-hmm.
And I guess with these kind of gradient penalties, you can enforce that the classifier varies more smoothly, and so this kind of uncertainty tells you something about how robust it is.
Can you explain the analytical approximation to noise injection that you use in your paper, and more specifically, how the Taylor approximation is used?
Sure. So we have seen that training with noise is equivalent to convolving the densities, but in general, it might not be possible to analytically convolve those densities, right? In the GAN, for instance, you don't even have access to the true densities, so there is no hope of being able to analytically convolve. But what you can do is you can Taylor expand the discriminator around, a noise vector xi equals 0, and then integrate over this noise. So that gives you then a kind of third order approximation of this convolved GAN objective, which is a third order approximation because all the odd orders integrate to 0 if your noise distribution has mean 0. So if you make a Taylor expansion, the first order Taylor expansion will be proportional to the noise vector xi, and if this has mean 0, this order cancels. Then the second order will be proportional to the covariance of the noise times the Hessian of the discriminator. And then again, the third order is again proportional to xi to the power of 3, and this cancels again because it's an odd order. So your approximation of this convolved objective will be accurate to third order. So the error you make is order 4.
Can you explain more about how the gradient objective is derived?
This derivation is really based on an ingenious insight by Chris Bishop in his paper, Training with Noise is Equivalent to Tikhonov Regularization. So what he shows is that you can simplify this objective massively if you evaluate it at the optimal discriminator. So in this case, the Laplacian terms cancel, and you're just left with a gradient penalty. I mean, you're just left with a regularizer that depends on the gradient norm of the classifier. And Chris Bishop derived this for the sum of squares loss and for the cross entropy, I think. One of the main contributions of our paper was to show that this derivation generalizes to any F divergence. And for this, we used a quite elegant property of the optimal discriminant that was derived by Nguyen, Wainwright, and Jordan in 2010 in a paper called Estimating Divergence Functionals. So again, we evaluate this objective, the general F-GAN objective at the optimal discriminant, and then these Laplacian terms cancel, and you're left with a regularizer that depends on the gradient norm of the discriminator.
What approximations go into that, or are there any missing terms that you potentially could handle to make it closer to injecting noise, if that makes sense?
Yeah, very good question. So I mean, you have this Taylor expansion that you truncate at some order. In our case, we truncate at order 4. So there is this difference between adding noise and the regularization that just comes from truncating this Taylor expansion.
Yeah.
But on the other hand, the error when you sample explicitly, also you need to sample a lot. So I'm not sure whether this truncation really has a big effect or not. The other, let's say, underlying assumption that we make is if you optimize this regularized objective, then you will come to this kind of optimal discriminator for which you know that these Laplacian terms cancel. So, I mean, this is what this Wainwright, Nguyen, and Jordan paper.
Yeah.
So for any F divergence, you can essentially write down what is the optimal discriminant. And then just using this kind of property, you can see that these Laplacian terms cancel, and you're left with just a gradient regularizer that depends on the norm of the gradients. Yeah. So really, maybe summarizing the whole derivation once again is you start with your GAN objective, you convolve it, and then you do a Taylor expansion, you truncate at order 3, and in this first truncated expression, you have Laplacian terms that are quite intractable to compute. But if you now make use of these properties of the optimal discriminant, you can show that these Laplacian terms simplify to gradient norm penalties. You just make use of this kind of property that if you know that this is the optimum.
Oh, then it gives you the true density.
Yeah, then some of the terms cancel and you can just use this more simple objective to optimize your GAN from the beginning, right?
The resulting objective that you get from this has the gradient term multiplied by, I guess, the value of the discriminator squared for the real values and
Right.
minus the discriminator squared for the fake values. And I guess some people have observed that the method still works without that term removed. And I guess the effect of that term is if the discriminator is saturated, it turns the gradient penalty off effectively, right?
Right. It's an interesting observation. So, I mean, the form that you're referring to is if you express the discriminator output as the sigmoid of the logits, right?
Yeah.
And then you will find that your gradient regularizer is kind of 1 minus the discriminator times the gradient norm of the logits. And this tells you if your discriminator is wrong or uncertain, then you should penalize more. And if the discriminator is correct, then you should penalize less. So I think it has kind of a nice interpretation. I think they do matter when you go to multi-class classification, because what you can do is you can generalize this regularizer that we propose to a multi-class cross-entropy loss.
Yeah.
And I think these weighting factors, they kind of tell you how to balance the different classes. So they might make sense in this scenario. It might matter because of this interpretation that if, let's say, the classifier is certain for some classes, but for others not, then maybe it should kind of penalize more for the classes where it's not yet certain enough, and the other ones where it's already kind of stable and sure, you don't care that much, right? So, well, maybe if it's just real versus fake and you only kind of change your generated, the fake distribution, then this weighting might not really matter. But if you generate different classes, then maybe the weighting matters because some of the ones you generated are already much closer to the true ones and the others are less. And so you penalize more on the ones that you're still further apart. So I guess that's where it could matter.
Could you comment on the overall reception your paper has had in the machine learning community?
Sure. So the first feedback we got actually came from Devin Young from Mila. Maybe you know him.
Yeah.
So he wrote me an email saying that it works quite well for even very deep ResNets and on language models. And then we also got quite good feedback at NIPS from people telling us that it works for them quite well. And also, we had this quite prominent feature. We were quite prominently featured on Ferenc Husar's blog.
Yeah.
So more recently, there has been quite a few emails of people asking whether we could share some pre-trained models with them.
Future outlook. Your work presents an analytical approximation to a method of injecting noise into a deep network as a way of reducing variance. Do you think there are other places where such a strategy could be relevant?
Quite recently, I have seen this paper. It's called Adversarial Vulnerability Scales with the Input Dimension by Leon Boutou, Shilkov, David Lopez-Paz, and Simon Gabriel. And in this paper, they also use this gradient penalty to protect against adversarial vulnerability. They make use of a quite nice, quite elegant extension, namely if you have the gradient of the discriminator times the adversarial perturbation and you look for the worst case adversarial perturbation, then this gives you the dual norm of this gradient. So what they find is to protect against adversarial examples, you should penalize the dual norm of your discriminator or classifier gradient. You have the norm, of the gradient times the adversarial perturbation. And now you look for the worst case of this perturbation. And then there is this inequality, Hölder's inequality, that tells you the kind of worst case perturbation, or the norm of this worst case perturbation is given by the dual norm of the gradient. So what they find is if you kind of start with a loss function that has a p norm, then you should find you should penalize with the corresponding q norm, this kind of dual norm, where 1 over p plus 1 over q is equals 1. So it's just kind of an interesting extension that you can use the dual norm for this gradient regularizer to help or to prevent adversarial vulnerability. You will, if you follow their paper, you will get the dual norm. So you penalize the dual norm in the case of, for instance, the dual norm of the one norm is the infinity norm. So if your objective has a one norm, then you're regularizing with respect to the infinity norm and vice versa. So if you're looking for the worst case infinity norm adversarial perturbation, then you should regularize the gradient one norm of your discriminator or classifier.
Now that we're on to it, another thing I'm curious about is, I guess you can look at the gradient penalty as a way of like variance reduction, or like it's doing something similar to injecting noise, but it has lower variance. Can you quantify how much it reduces the variance of the estimator, or?
Why do you think it should reduce the variance of the estimator? So you mean the gradient penalty or injecting noise?
What I mean is, if you think about the effect of injecting noise on what your estimator is, you're going to have to inject noise a lot of times to cover all these directions in the space versus just having to do gradient penalty.
Right.
I guess what I'm curious about is how much the variance of like the gradient estimator differs when you do gradient penalty versus when you inject noise. Does that make sense?
Yeah, the question makes a lot of sense. I mean, I can't give you an answer to this except that, I mean, in the GAN case, we looked at the visual quality of the samples. But
I mean, if when you compute your gradient, if you were injecting noise, what you could do is you could inject noise like k times with a different noise thing each time and get your gradient by averaging those.
Right.
And then for a very large k, maybe the variance becomes okay, at least in low dimensional problems. Whereas with the gradient penalty thing, you just run it once. So, I mean, it's not like I've gone into the math of it or anything, but I'm curious. Maybe there's a way to prove like
it does sound
changes.
It does sound like a non-trivial question. I mean,
intuitively, it seems like it should scale with like the dimensionality of the space, I guess. For another question, what do you think of the utility of gradient penalty beyond GANs?
What is interesting is this kind of connection between regularization and generalization and the capacity of the neural networks.
Yeah.
So there was this talk by EYT at NIPS where he said that, the parameters in neural networks are non-identifiable and you should rather think in terms of function classes. And I think this is maybe where these gradient penalties could come into play, that what you're essentially trying is to have a kind of prior on the function that your neural network represents. And this prior should maybe not depend on the parameters, but instead directly act on the function class itself.
That makes a lot of sense to me, because like how much you change a certain parameter is going to depend, or how much impact that has is going to depend on what all the other parameters are.
Exactly. And also there is a huge kind of weight space symmetry and all stuff that the ultimate question is kind of why do neural networks generalize and how can we control what kind of representations these neural networks learn, right?
Right.
And if these gradient penalties somehow give us a handle on what these neural networks learn. So something that I observed with this GAN work is that if we use this gradient penalty to train a ResNet, for instance, and then look at during training consecutive images generated by the generator, then what you can see is that with the regularizer, the discriminator is focusing on something semantically meaningful. So you could see, for instance, images where in one image the lights were turned off, and in the next image the lights were turned on. And then you can see the same image with some paintings on the wall. And the next image has the same structure, everything, just different paintings on the wall, and stuff like that. So I found that quite interesting. Whether, this kind of gradient penalty allows the discriminator to focus on something semantically meaningful, some kind of more high-level features rather than just low-level patterns. And then one other direction, I think you wrote a quite beautiful paper on this, the discriminative regularization, where you investigate, can we use a kind of discriminator to regularize, like a VAE, I think it was in that case.
Yeah.
So that the distance with which you compare the decoded with the original sample is not this kind of L1 or Euclidean metric, but instead it's this kind of discriminator-induced similarity metric, which I found quite interesting.
So one thing I'm actually curious about is maybe if someone is interested in getting into like GAN stability research, do you feel like a lot of it is solved, or what do you feel are like the big open problems?
The whole stability issue is really connected with generalization. So maybe you should look at robustness simultaneously while looking at how well do these models that you train generalize. Distributionally robust stochastic optimization, where the people say, you don't want to actually learn a classifier model from the empirical data, but instead you want to learn it from some, let's say, worst case distribution Q that is close to your empirical, but it's not exactly the empirical one. So that
I see.
You kind of hope to be robust with respect to some changes in your empirical data.
That's interesting. It's not obvious to me how you define the other classes that you want it to be robust to, or the other distributions that you want it to be robust to. Like in the adversarial example stuff, that literature, they just like put this little epsilon ball around like every data point, and they make the epsilon ball really small, and they say like, well, like of course within this little epsilon ball it's like imperceptible, so you want the class to be the same, but in general having like richer definitions than that is not obvious to me how you do that.
Right. So perhaps one of the key issues is really how to kind of model human similarity, to have kind of metrics that allow us to measure when two things should be the same and when they should be different.
Aside from your own work, what do you think are the most interesting directions in generative modeling research, or like what your thoughts are on this spectral normalization paper? Their whole thing is like you can guarantee this Lipschitz continuity by bounding the size of the largest eigenvalue.
Right, yeah.
So their whole argument is like, maybe you want to apply regularizations to the discriminator that make it like Lipschitz continuous, but you don't necessarily want to push down the rank of your matrices. I don't actually remember if, so they have an argument that like weight normalization pushes down the rank of the weight matrices.
But what they said is that the weight normalization is kind of a Frobenius norm, which they argue, pushes down the rank of your approximation, but the spectral norm doesn't. So then you can retain more of these kind of singular values and singular directions.
So even just as an empirical observation, it might be cool to run, even just like on fully connected nets, run with gradient penalty and run with spectral norm. And when training is finished or progressed or whatever, just do the SVD of your weight matrices and then see if in practice, like gradient penalty has pushed down the rank.
That would be super interesting, I agree.
Yeah.
And also it could be related to the problem of mode collapse. So if you think of modes in terms of kind of singular values, maybe, and maybe you can show that with this kind of regularization, you prevent, the kind of rank from becoming too small and thus dropping too many modes. If you want to learn a robust classifier, does that necessarily involve learning a generative model? Because, for instance, in these adversarial samples.
Hold on. You said to learn a robust classifier?
Yes.
Yeah.
Does learning a robust classifier necessarily involve learning a generative model as well? Because in these adversarial sample cases, I mean, the classifier can easily be fooled by a perturbation that is not even perceptible to a human, right? Does this have to do with the fact that the classifier needs some kind of intuition about the distribution of the samples and not just being able to perfectly classify the test set?
It's not obvious to me that a generative model solves the adversarial example problem.
But at least if you know, like, whether this sample that you're just now seeing comes from the tail of your distribution or whether it's from the bulk, gives you a more kind of robust classifier, right?
Like with humans, we don't really learn generative models of detailed things in the world, even though we learn to do recognition. So, for example, with the Chinese language, the way they write it these days, like with computers, is they have like an autocomplete system. So they just have to like type this, it's called like a pinyin description, and then pick the character that they want. So when you start doing that, you can forget how to actually write out the character. And the only point I'm making is like like for humans in that case, the recognition capability is stronger than the generative capability.
So you mean that people can still read those Chinese characters, but in order to generate, they just need to know the pinyin, but not the actual.
Yeah, they don't remember how to generate it in detail.
Right.
They don't remember how to write it.
That's
but
interesting.
They remember how to recognize. Yeah.
So it means you more directly generate the kind of hidden representation or some kind of latent embeddings instead of actually generating the characters itself.
What do you think is going to happen to machine learning as a profession?
Right. So I think, or my optimistic self thinks that machine learning is going to become part of a toolbox, just like statistics is one.
Yeah.
And some people even say that machine learning might become the lingua franca, so the kind of unifying language that connects different sciences and so on.
Yeah.
And I think with recent news about how IT companies, mishandle all our data and stuff, it's really great that people like you have these kind of are trying to bridge the gap between, what people know about research and what we do in research and, how it's kind of perceived in society, what we do.
Oh, it was great having you as a guest.
Paths will cross in the future.